There are certain indeterminate forms in mathematics, things that are such that, for example, the limit of the top and the limit of the bottom are both 0, or the limit of the top and the bottom are both infinity, or the limit of 1 is infinity and you're subtracting another number which is also going to infinity, or one number is going to 0 and another number is going towards infinity and you're multiplying them, or one number is going towards 1 and the other is going to infinity and there's exponentiation involved. Each of these can turn into an interesting puzzle in mathematics. And there's a famous and very useful rule for dealing with it. It's known as L'Hopital. So L'Hopital's rule states that if it's of the form 0 over 0, or if it's of the form infinity over infinity, then the limit as x approaches the value in question of the ratio is equal to the limit of the ratio of their derivatives. And this is something that allows us to find certain limits much more efficiently. There is the restriction here that g prime of x can't be 0 on this open interval which includes a, but this clause doesn't necessarily have to fit a itself. It just has to fit those values close to a. So let's take a look at a very simple example that we already know the answer to. The limit as x goes to 0 of sine x over x. Earlier in the course we had two triangles and a wedge, and we used the squeeze theorem, and it was a long and complicated proof culminating in the fact that the limit as x goes to 0 of sine x over x is 1, so long as we're dealing with radians. Now, I've got a much simpler version. This is of the form 0 over 0, because as x goes to 0, sine of x is going to 0, and x is going to 0. So this should equal the limit as x goes to 0 of the derivative of the top, which is cosine of x, over the derivative of the bottom, which is 1. Since the bottom is no longer 0, it's tempting just to plug in x equals 0. And when we do, we find that this is equal to 1. And so we get the limit as x goes to 0 of sine x over x is 1, without the lengthy argument. I do have one favor to ask. Now, because this equality is based off of an application of L'Hopital's rule, whenever you use L'Hopital, I would like you to put an L' H above the equal sign, so that I know that you're saying that this is equal to this by L'Hopital.